really sure this is a good idea. Okay, I'll put the script. And he will be presenting two-party ECDSA signing and constant communication overhead.
Thanks for that introduction. Hi, yeah, I'm Yash. I'll be speaking about my paper on two-party ECDSA signing and constant communication overhead. You can find it on ePrint. There's also this QR code. And yeah, it's going to appear here in the presenter. Yeah, this is working. Okay, so the setting for this talk is going to be two parties that are executing some sort of signing protocol, and this corresponds to many deployments. I will not be talking about the actual deployment of this protocol today, but yeah, that's the setting. And the sort of broad premise, if you're roughly familiar with this area of threshold ECDSA signing, is that it's been studied for a while now, it's safe to say, and it still seems that distributing ECDSA signing amongst a group of parties, even two parties, is substantially more complex than just plain ECDSA signing. Right? So given that the use cases of threshold signing are growing quite a bit, that is already in the cryptocurrency setting and beyond, it is important to consider whether this overhead is inherent or whether we can get the overhead of two-party signing down to something that's closer to plain signing. And yeah, so that's a question that we study in this paper, to what extent can we actually get the overhead down? And we show through a new construction that we can actually get close to to plain signing in terms of asymptotic overhead, so constant overhead in communication. And for a standard signing curve that's about 256 bits, we get communication on the order of, like 170 bytes, less than a millisecond per party in terms of compute time, and just a pair of messages, so send and get back. So a very minimal communication pattern as well. And we achieve this using just ECDSA native tools, so like generic tools. And I'll say more about this through the talk. So this is a quick reminder. This is the sort of rough type of use case that we start with. That is our friend Bob, who has a bunch of Bitcoin, and when he wants to send Bitcoin to his friend Alice, essentially he hits a button on his laptop where he has a signing key. He generates a signature, attaches it to the message, and that lets Alice claim her key and be on her way. Sorry, her Bitcoin and be on her way. But let's say for no fault of Bob's own, turns out that maybe the operating system that he's using has some sort of bug. So an attacker could turn up, break Windows, and do something complicated to get the key out, and forge all kinds of messages and steal Bob's funds. And this is a bad situation. So instead, Bob could employ distributed signing, which is to say that he takes his key and he splits it into, let's say, two halves, and puts each half on a different device, and then executes a distributed protocol to sign messages instead of reconstructing the key at any individual place. And the idea is to distribute the risk of compromise. And we can also consider scenarios where there are extra backup shares. So in case one of the shares is gone, you can still recover the signing key. Right, so ECDSA, or the elliptic curve digital signature algorithm, was devised in the 90s and has been standardized for a while now. And importantly, it differs enough from Schnorr, which was patented, that it was able to get around this patent and find wide deployment around the internet. But unfortunately, the way in which it differs from Schnorr has meant that there have been new issues created for, let's say, threshold signing. So the first half of ECDSA looks a lot like Schnorr structurally. And the first half, that's just sampling a nonce, is a fairly well-studied problem, so I'm not going to talk about that too much. And it's the second half of these two algorithms in which you can see that they kind of diverge, whereas Schnorr has this simple linear function that combines the secret elements involved, so it's very MPC friendly and so forth. ECDSA has this strange nonlinear function. which we can get into. So essentially, there are two secrets that go into the signing equation for ECDSA. And these secrets are multiplied, which is one like strange nonlinear thing, as in they have a multiplicative relationship. And also there's this division involved. You can see that there's a secret in the denominator, which is bad news for MPC. And it's become clear at this point that computing ECDSA in a distributed way, it can be reduced to a classic MPC primitive. And both good news and bad news that we don't have a clear winning instantiation for this primitive. It can be tuned for the deployment. In particular, the primitive that I'm talking about is secure two-party multiplication, also known as oblivious linear evaluation, or OLE for short in the literature, also much to add in some papers. And it underlies many protocols in this dishonest majority setting, like the two-party setting. Essentially, it allows the sender to input two values, alpha and beta, and the receiver to input x, and obtain alpha x times beta as its output. And there are efficient constructions for this primitive from a number of different tools, like OT if you want to be generic, PyA or class groups if you prefer something based on homomorphic encryption and so on. And I've taken a few representative works across the literature that signify sort of different points in the trade-off that you can make in computation and bandwidth to achieve this tool of OLE. It's not the exact numbers don't matter so much, but what does matter is that each of these tools in every dimension is substantially worse than plain ECDSA signing. Right? So to put this into perspective, I've plotted over here, this plain ECDSA signing, the computation involved to create and verify a signature, and bandwidth and the two axes. And I've plotted all these representative works in different points in the graph, and it's clear to see that in both dimensions, it's orders of magnitude worse to use any of the two-party signing protocols relative to just plain signing. Right, so it's clear at this point that there's a substantial overhead. But if we want to see wider and wider deployment of two-party ECDSA signing, we need to think about how inherent this overhead is and can we get around it. I mean, it's clearly already enough, or there are applications where the cost of this decentralization is worth it, given that it is already, we do already use two-party signing in practice. But if you want to scale to, broader audiences, different applications beyond cryptocurrencies or even cryptocurrencies and stablecoins and so forth that are used on a much larger scale, as we expect them to be, then we need to consider whether this overhead is, inherent. So, right, that's the main question of this work. And we can think of breaking down this problem along, to begin with, just asymptotic complexities, right? So, asymptotically, it takes on the order of linear number of bits in the security parameter to transmit a signature, and a constant number of operations, at least in terms of elliptic curve operations, to compute one. And this already tells us that the approaches that we have in the literature are maybe not the best, because OLE, which is that fundamental building block, already exceeds these complexities, right? So if we consider just communication complexity, all the approaches that we know of for OLE, that I know of, that you can do in this single standalone setting without extra setup and so forth, have at least a quasi-linear communication complexity through OT, and depending on how you characterize the hardness of different problems that you can build homomorphic encryption from, it's for sure superlinear in the bit size, in the size of the security parameter of homomorphic encryption. Right? And computation is a lot harder to characterize meaningfully because it involves combining different primitives, so I'm going to stay off of computation for now. So yeah, just communication alone, there's already this seeming bottleneck. So we have a new framework in this work, which does hit the same asymptotic complexity as ECDSA, which is linear number of bits in the security parameter. So this is now constant overhead for two-party signing as opposed to plain signing. And concretely, the constants are pretty good. You can think of this as a couple of ECDSA signatures sent and received for two-party signing. And at the same time, we also achieve the best known computation, about 1.6 milliseconds on our benchmarks on a standard MacBook. So this is still about an order of magnitude slower than plain signing, but yeah, maybe we could do better in the future, who knows. Right, and the tools that we use to do this are not fancy at all. They're the most basic things. Essentially, signing just involves PRF invocations, and this means that we can then benefit from hardware acceleration on most platforms. In fact, even our implementation uses AES and NI very extensively. And and key generation also uses only generic tools. It can be used it can be instantiated with just Diffie-Hellman in the signing curve, basically to get oblivious transfer. Right, so to put this work in perspective, essentially on both dimensions, it gets closest, a lot closer to plain ECDSA signing as was previously known. Okay, so how do we actually construct this, right? So our starting point is what is in some ways already quite close, the closest trade-off the most interesting trade-off that's been made previously, which is this work of Lindell, which is optimized for the two-party case. I'm going to use this framework for interpreting threshold ECDSA protocols that we had in this prior work that kind of retrospectively interpreted each protocol along a few axes. So the first step in the recipe to construct a threshold ECDSA signing protocol that we written down was to first rewrite the ECDSA signing equation to be MPC friendly in some sense, like to avoid the second verse and so on. And the next step is to then construct some sort of cryptographic machinery to actually securely compute this rewritten equation. And then finally, we need to verify that all the operations were performed honestly. Right? This is just like a heuristic way of characterizing protocols in the literature. So if we take this Lindell scheme, the first step is to use what I would call a multiplicative rewriting of ECDSA. And then the machinery that's used to compute this equation is a pi-a based OLE. And I'll talk about these two now. So there has been this interesting way of rewriting ECDSA that I think originally goes back to Mackenzie and Reiter, and then has been refined progressively through different works, including Lindell's and most recently this paper by Ajaj et al. So these are the two interesting terms from ECDSA. Right? There's this public nonce capital R, and then there's the actual scalar that's this exchange nonlinear combination of these values. So I'm going to split the secret terms into multiplicative shares. That is, the signing nonce k split into k0, k1. Sk is split into sk0, sk1. That's the signing key. And I'm just sort of cleaning up the notation a little bit. Basically, I'm rewriting this equation so that I'm able to separate out multiplicative shares that can go to each party in the two-party signing protocol. Right? So I've rewritten S as S prime by K0, and read it in S prime as just this much cleaner term alpha Sk0 plus beta. Right? I mean, just trust me that I've done this correctly. The idea here is that I can give the 1 subscript values to party P1, the phone, and the 0 subscript values to party P0, that's the laptop. And then there's the last thing that remains to complete signing an ECDSA signature is this S prime value. Once we have S prime, we're good to go. Right? So if you think about it for a minute, it becomes clear that you can safely reveal S prime to party P0, like S prime to the laptop in this case, because it's a deterministic function, or it's a deterministic value once you fix S and K0. Right? So it's clear that you can reveal S prime. And essentially, this is where the OLE comes in. Everything so far has been simple linear operations. Now we need to use an OLE to compute this S prime term, and that's the focus of this. Like if there's a bunch of math that goes in, that's not super interesting. The interesting thing cryptographically is the fact that we need to use OLE to compute this S prime value, which exactly realizes this correlation that we need. All right, so what is the structure of this OLE? Lindell's protocol follows this classic template Utical Boa that's based on pi-a encryption, or really realizable with any additively homomorphic encryption scheme. Right. At a high level, basically, the laptop in this case, that's the OLE receiver, sends SK0 encrypted, and then the phone sends back this linear function using the homomorphism of the encryption scheme. Like it leverages the additive homomorphism to compute the output, like compute an encryption of the output, which then the laptop decrypts. This is, again, I'm hand-waving a lot of details here, but this is the high-level idea. And what Lindell observed was that the first message of this protocol, which encrypts the signing key share SK0, is common across all executions. Right? SK0 stays the same across all signing instances because it's not dependent on the message. And so what you can do is execute the first message during key generation, and then every time you want to sign a message with ECDSA, you execute the second round reactively of the OLE protocol. And one of the things that I'm sort of hand-waving here is that the first round needs some additional checks, which is what makes it really heavy, and which is what makes this like a really useful saving in practice, that you can pre-process this first round. And so our first step is to generalize this concept. Right? This is the way that Lindler written it was very specific to Bayes encryption scheme. So I'm going to rewrite this using some abstract tools. That is something that we call reactive vector oblivious linear evaluation in this paper. What is this, right? So vector OLE or VOL is a well-known primitive in the literature. Essentially, it allows a sender to now provide a vector of inputs rather than a single input, and then the receiver has its own input fixed. And it's well known that doing a vector OLE of size n, like with a vector of size n, is going to amortize a lot better than doing n individual instances of OLE. Right? So this is vector OLE, and the reactive component of this is that the sender's vector can be extended on demand. Essentially, every time I want to sign a message, I'm going to extend the size of the vector that the sender puts in. Right? So it's a reactive mode. And now that we have this abstraction in place, we can now think about simpler ways of instantiating this. And what we show is that indeed you can do setup with just OT, and you can instantiate the send operation with just any PRF and just some arithmetic in small fields. This is the underlying insight that enables our result, which is that we now don't need full-blown OLE to do two-party ECDSA signing. We can use a much simpler tool, which is just this reactive VOL thing. And the starting point for how to actually instantiate this reactive VOL is to look at this OT extension paper by Roy from 22, which gives what is effectively an R-VOL for ZP, like integers modulo P, where P is small. Small means asymptotically polynomial. And this actually already fits the structure. Sending is non-interactive, and you only need PRFs and so forth. But the reason why Roy's construction doesn't give us what we want is that it works only over small fields, but we want this for a large field. Right? It works with ZP. We need ZQ, where Q is a curve group order, basically. So how do we boost a small field VOL to a large one, right, is the question. And I mean, if you're familiar with the Chinese remainder theorem, this is a classic way of emulating large integer arithmetic using small integer arithmetic. So if we take a bunch of VOLs instantiated over small primes, we can then compose them to get a VOL over a large primordial modulus. Basically, that's just the product of all these primes. So this is, in some sense, a known technique, in the sense that there is precedent for this technique. There has been OLE that's constructed using leveraging the Chinese remainder theorem in previous works. But yeah, so what we do is we start with this no communication PRF based R-VOL for small primes, compose a bunch of them, get it for a large modulus M, and then we de-randomize this VOL into what we actually need, which is VOL over modulus Q, like a prime modulus Q, large prime modulus Q. So what is the structure of the computation? It's not, I'm not going to write down the exact protocol of Roy's, but take it on faith that it's like very simple PRF evaluations and additions. It's something like you evaluate a PRF p times and then you just add up like all these PRF results. Or like in some case you do some weighted sums, but it's very simple tools basically. Right, and I mean, in case you're interested in this kind of thing, what we also get is, as a byproduct, is a pseudo-random correlation function, or a PCF, for vector OLE over a large ring. So to sort of zoom in on the problem a little bit, essentially the CRT R-VOL only works for smooth M, but Q is prime. So we need to securely translate a correlation over a large, like a VOL correlation over a large modulus M into one that works over this prime Q. And VOL de-randomization is a fairly standard thing, like you just sort of publish the difference between a chosen input and a random input. The important thing for this particular de-randomization is that we really need the correlation to hold over the integers. So we take a correlation over a large modulus M and then reduce it mod Q and hope that it still works. And it still works as long as we haven't overflowed over M. Right? In order for this to be true, we just need to make sure that all the values involved are less than a certain range, like range bounded. Right? And I'm going to call this event good, A alpha beta X. And it's trivial to enforce good alpha beta X by just making sure that all the inputs are of the correct range. So at least for the semi-honest case, we are done. Like, So if you sort of work out the parameters, you basically get that m is like the bit length of m can be linear in Q, like bit length of m is linear in bit length of Q. So we get now a communication complexity which is the same as ECDSA itself. And yeah, for a 32-byte curve, we get like an 80-byte message for the R goal essentially. So that's our goal. And the last step of the recipe is to verify that the signature is well formed essentially, and this verifies that all the computation is done honestly. And we sort of take Lindel's strategy and just generalize it. So we also inherit these like caveats. Essentially, we want this good primitive to hold, this good predicate to hold. And while we can verify that X is well formed, this is the sort of special encryption scheme that Lindell uses, but we do it generically, where we can verify X during setup. Alpha and beta are implicitly verified to be good just if the signature verifies. And we sort of take Lindell's analysis, generalize it, and show that you can reduce security to just ECDSA by predicting, like, if this good predicate doesn't hold in one of the sessions, we can just guess which session and abort accordingly. The proof details that not super important right now, but I can talk about later. Yeah, and that's the machinery, and then we have the machinery plugged into some sort of method to actually sample the nonce, and then that gives us a full signing protocol. So 3 rounds with uniform nonces, 2 rounds with biased nonces, and we save some bytes to some special assumptions in some cases. Right, so that gives us a 2-party signing protocol that gives us constant bandwidth overhead relative to just exchanging ECDSA signatures. And the insight was to relax the primitive that we use and show that it can be instantiated with weaker assumptions and weaker tools. And concretely, we get the best bandwidth and computation simultaneously in the literature, and this is the closest we've gotten to plain ECDSA signing. Thanks.
Oh yeah, it will be. So the question was in regards to this slide that you have an abortion procedure, and if you are going to be aborting then all of the future sessions with those incorrect values.
So we kind of did like an apples to apples thing with Lindell's protocol with the analysis. So we can, the way that this protocol works now, you have to rekey if you see an abort. But like if you inflate the bandwidth like a little bit, still constant overhead, you can get rid of this as well. So you'd have to re-randomize your state, but
Yeah, and is it a hard result that you can only check the alphas and betas at the end in the signature? There's no way to check in between?
That's a good question. So there are generic tools that are a little complicated. So it's not easy. I think we need to do something more complicated to do that generically.
Okay. Any other question? Okay, if not, let's thank the speaker again.